In this video, we're going to look at ways to find the sum of infinite geometric series. And we're going to do so by doing the geometric series test. And we're going to kind of confirm these sums, or whether or not the series converges or diverges, by looking at the graph of the partial sums in Desmos. And so an infinite geometric series, or a geometric series in the form starting with n is equal to 1 and adding an infinite number of terms together, or seeing what the sum approaches, of the explicit form of a geometric sequence, a1 times r to the n minus 1 power. The geometric series converges by the geometric series test if and only if the absolute value of r is less than 1. So if the absolute value of r is less than 1, then the sum of the series will be equal to the first term divided by 1 minus r. Now, it's also important to note that if the absolute value of r is greater than 1, the series is going to diverge, which means that there is no finite sum. So we want to look at each of these geometric series and determine whether or not the series will converge or diverge by the geometric series test. So looking here at this first problem, I am looking at the series, and I look, and this is a geometric sequence here on the inside. And so really we're looking at an is equal to -1 times -3 raised to the k minus 1 power, which what I want to find is this series will converge if the absolute value of r is less than 1. Well, r in this case is equal to -3. So r equaling -3, the absolute value of -3 is greater than 1, which means that the series will diverge according to the geometric series test. All right, so here I'm graphing this geometric series, and I have the terms plotted for the sequence. Now, we're looking, and remember how the nth term test worked for previous videos, that if the limit of a of n did not equal 0, then the series itself was going to diverge. Well, if I'm looking here, as I'm working my way in terms of my sequence values, and I'm getting larger and larger values for n, I'm not approaching a certain value. The limit doesn't exist, because in one instance I'm heading towards positive infinity, in another instance I'm heading towards negative infinity. Now, looking at the graph of partial sums, well, that'll be here in red. I look at the graph of partial sums, and what I have is I'm looking, and the graph of partial sums don't converge either. As the farther I move to the right, the more these values are becoming separated, and they're not narrowing in on a certain value, which means that it diverges. Now, we saw that with the geometric series test. All right, let's look here at this second problem. So I'm given the first handful of terms, and I want to know, will this series converge or not? If it does converge, what is its sum? Well, I need to figure out what r is. What's the pattern here to get from one number to the next? I'm multiplying by 1/5 each time. So that means that r is equal to 1/5. Well, this is a geometric series. It's a geometric series because I'm multiplying by one number to get to the next every single time. And so what it's telling me is that since the absolute value of r is less than 1, the absolute value of 1/5 is less than 1, this series will converge according to the geometric series test. What it means is, if I write this using sigma notation, so the sum from n equals 1 to infinity of this geometric series, which would be written in explicit form as 3 times 1/5 to the n minus 1 power, that's going to equal a sum of a1 over 1 minus r. Well, the first term is 3, and r is 1/5. And so it's going to equal 3.75 is what the sum's going to approach. All right, so graphically, if I graph the sequence itself, we'll look and see that the limit of the sequence now I'm talking about the sequence of terms, not the series, the sequence of terms approaches 0. And which means that it passes the nth term test. Now, if I plot the series of partial sums and look at graphically the partial sums here, as I add more terms, my sums are getting closer and closer and closer to, well, they're staying 3.75 is what they're heading towards, which is the same value that we estimated as for this infinite sum. All right, let's look at this next one. So I want to know, well, will this series converge or not? Now, before we go through the process of doing it by hand, I'm actually going to look at the graph here on Desmos first. So I've plotted the sequence that it lies inside, and I'm finding the sum of A of n. I look here in purple, and that sequence is approaching as n increases or heads towards infinity, the number of terms, the value of the sequence is approaching 0, which means that it passes the nth term test. So since the limit of the sequence is equaling to 0, I have to find some other way to determine if this series will converge or diverge. So we'll look at the plot of the partial sum. So let me turn it on here in red, and I need to zoom out a little bit to see what is happening. And so here in red, we look, and notice how it flattens out. And so as we're working our way to the right, and adding more and more terms together, we see that the sum, as we're starting to add more and more terms, is getting really close to 259.2. So we see that it diverges, we see that it converges, and that the sum is approaching 259.2. Well, how can we get that? By using the geometric series test. What we would need to do is we would need to write this in the form of a geometric series. So we're going to use some properties of exponents to do so. So we have 9 to the negative n plus 2 power times 4 to the n plus 1 power. Well, what I can do is I can pull a negative out of that n, the 9 to the power exponent, and that'd be the same thing as 9 to the negative 1 times n minus 2 power times 4 to the n plus 1 power. And then I could rewrite that, because the 9 has a negative exponent, as 4 to the n plus 1 power over 9 to the n minus 2 power. And then we could say, all right, well, what do we have here? We're going to continue to use some properties of exponents and say, all right, well, that's the same thing. 4 to the n plus 1 power is the same thing as 4 to the n times 4 to the 1. And then 9 to the n minus 2 power is the same thing as 9 to the n times 9 to the negative 2 power. So what I can do is I can take that 9 to the negative 2 up top. Well, 9 squared is 81, and 81 times 4 is going to give me 324. So I'd have 324 times 4 to the n over 9 to the n, which I could go one step farther, since both the 4 and the 9 have the same exponent power, and say that same thing as 324 divided by, or times 4 over 9 raised to the n power. Now, what we've done is we've written an equivalent form of this. Well, that's geometric, because I see the exponent power, or what the exponent is being applied to, in this case n, and that's being applied to 4/9, which means 4/9 is r. The absolute value of 4 over 9 is less than 1, therefore this series will converge according to the geometric series test. So since it converges, I can find the sum. Well, what we've done is we've written an equivalent form of this summation, where we go from n is equal to 1 to infinity of 324 times 4 over 9 raised to the n power. Well, that sum would equal the first term over 1 minus r. Well, the first term is going to be, what do I get when I put in 1 for n? Well, that's 324 times 4 over 9, which gives me a first term of 144% in terms of this series. So we could find our sum by saying 144 over 1 minus r, 1 minus 4 over 9. And to get that, we get 259.2. All right, let's look here at this next one. So finding the sum of the series, an infinite series from n is equal to 1 to infinity of this expression. Now, in order to do this, I would need to see if I could write this in geometric form, since I'm seeing that I have n and into the exponents. So we need to use some properties of exponents here. So I have negative 4 raised to the 3n power, and then we have that 5 raised to the n minus 1. Well, we're going to start using properties of exponents, and we look and say, all right, well, I multiply my exponents when I have a power raised to a power. So we'd have negative 4 to the third power raised to the n divided by, and then 5 to the n minus 1 is the same thing as 5 to the n times 5 to the negative 1, which if I take the negative 4 and I raise it to the third power, we get negative 64 raised to the n over 5 to the n, and I could take this 5 to the negative 1 up top, so I have a 5 here. And so if I continue to rewrite this, I have it in the form of 5 times negative 64 over 5 raised to the n power. Well, that's in geometric form, which means that I could apply the geometric series test here, and we look and r is equal to negative 64 over 5. Well, the absolute value of negative 64 over 5 is greater than 1, which means that it diverges according to the geometric series test, which tells me that I do not have a finite sum. All right, so graphically, if I plot this sequence to see in terms of individual terms, we start off, now look at my scale here. My vertical scale is, I really had to zoom out here, and by the time I reach the fifth term, my values are so spread out in terms of fifth term and sixth term that my sequence itself is not approaching 0 as n increases, which means that it failed the limit test. And since that limit of the sequence did not equal 0, it means the series has to diverge itself. Now, according to the geometric series test, if I looked at the sum of the partial sums, if I can even see them, what you're going to notice is that as you start to add more and more of these things, the sums are not converging either, which is what we saw by in terms of the sum being divergent. All right, one more example here. Let's say that I'm telling you that I have an infinite geometric series and I want to just find the common ratio. And they tell me that the sum is 10 and the first term is 4. Well, according to the geometric series test, that means that the absolute value of r has to be less than 1. And if that was the case, it converged. Now I know it converged because they told me the sum, and that the sum would equal a1 over 1 minus r. Well, the sum is 10, the first term is 4, we just need to solve for r. So I could multiply 1 minus r to the other side, and I get 10 minus 10r is equal to 4, which means I get 6 is equal to 10r, divide by 10, you get 3 over 5 to equal r. So that was the common ratio.